So it's a pleasure to introduce the next speaker of our seminar, Anton Galaev. Yeah, he's one of the co-organizers of the seminar. So we are happy to have to read his recent work with Dmitri Alekseevsky on conformally homogeneous Lorentzian spaces. Please, Anton.
Thank you very much, Van. Thank you for the introduction. So, as one told, this is a joint work with Dmitri Alekseevsky, and we classify conformally homogeneous Lorentzian spaces that are not conformally flat, and we show that in fact those spaces are exhausted by homogeneous plane waves. Let me start first explain the result. Consider conformal pseudo-Riemannian manifold. So we have a manifold and we have a conformal class of matrix C. A diffeomorphism of the manifold is called conformal transformation if it preserves this conformal class. So it means that f acts on arbitrary metric G, and we get another metric G proportional to the initial one. And f, this conformal transformation f, is called non-essential if there exists some metric in the conformal class such that f preserves this metric. So f is in fact isometry of some metric. Moment. Can you see the line after that? Yeah, yeah. So
yes, we can see it.
Yes. Otherwise, f is called essential. It is non-essential if it preserves some metric. But if f doesn't preserve any metric in the conformal class, then it is called essential. And similarly, subgroup of conformal transformations is called non-essential if it consists of isometries for some metric h from the conformal class, and otherwise it is called essential. So it is well known that any Riemannian manifold which admits essential group of conformal transformations is either conformally equivalent to the standard sphere or to the Euclidean space. This is a so-called Lichnerovich conjecture solved by Alekseevsky, Obatov, Ferrand. And at the same time, there are many examples of Lorentzian manifolds with essential conformal group. The example is constructed by Franz, Melnik, Zajib, and first examples of essential conformal homogeneous Lorentzian manifolds were constructed by Podaksionov, and also there is a description of Lorentzian manifolds with essential group of homotheties. Next, so we consider conformally homogeneous conformal Lorentzian manifold. So group G acts on M transitively, and it consists of conformal transformations. And we assume that G is essential. So it doesn't preserve any metric in the conformal class. H is a stabilizer of some point, stability subgroup of some point. Then we have a corresponding representation of H in the tangent space. And we consider two possibilities. First case, when, in fact, there are two possibilities. First case, when the isotropy representation of the Lie algebra H of the group H is non-faithful, so G is not injective. We denote by V the tangent space to the manifold M, and it can be considered identified with this factor of Lie algebra G of the group G by Lie algebra H of H. And another possibility is that manifold has faithful isotropy representation. So this map J is injective. And the first type of spaces was classified by Alekseevsky in 2017. And in particular, those manifolds of type A are conformally flat. So now we assume that J is injective, this map is injective, or we just may assume that our manifold is not conformally flat. Now, what is a plane wave? Plane wave is a Lorentzian manifold, MG, which admits a parallel vector field, P, which is also isotropic. So there exists a vector field P, parallel with respect to the Levi-Civita connection, and it is isotropic. And additionally, the Cauchy tensor of plane wave must satisfy two conditions. So R of xy is 0 whenever x and y are orthogonal to P. This condition, in fact, a condition for MG to be PP wave. And if PP wave additionally satisfies this condition, then we have a plane wave. And metric of any plane wave has the following simple local form here. So there are dimension of manifold is n plus 2. So we have coordinates v, u, and xi, I from 1 to n. And the metric depends only on the matrix, on the symmetric matrix, depending on one function u. So we have matrix of functions. And in particular, such metric is conformally flat if a non-leaf. So this is just identity matrix times some function of u. And also, if those functions don't depend on the variable u, then this is a metric of a symmetric space, Kain-Wallach symmetric space. In fact, Lorentzian symmetric spaces, indecomposable Lorentzian symmetric spaces are exhausted by de Sitter space, anti-de Sitter space, and Kaulach-Wallach symmetric spaces. Now, there is a first there is a classification of locally homogeneous plane waves by Blau and Olin 2003, and last year, and it was very, very important for us. So Janis Zajib, who is here at the lecture with co-authors, they obtained global results. So they classified all simply connected, so global homogeneous plane waves, simply connected homogeneous plane waves. And those spaces can be divided into two parts. In the first case, the metric is not geodesically complete. In the second case, metric is geodesically complete, and both metrics depend on two matrices. B is symmetric constant matrix, and F is constant skew symmetric matrix. So here we have classification of homogeneous plane waves, simply connected homogeneous plane waves. And there is also another very recent paper by Holland and Sparling, and they considered some conformal transformations of plane waves, and in particular they proved that those two spaces are conformally diffeomorphic. And if we consider the second metric and make this change of coordinates, you see that coordinate u now u is here u belongs to R, and EU is positive, so it gives us the coordinate here. So after this coordinate change for the second metric, we obtain this metric, which is the first one, with some modified b. So both spaces are conformally diffeomorphic. Also note that when we consider arbitrary plane wave metric, then there is a group of homothety transformations. If we change coordinate v to lambda square v, xi to lambda xi, And if you don't change coordinate u, metric g changes to lambda squared g. So all homogeneous plane waves. When I say homogeneous plane wave, sorry, it is homogeneous with respect to the group of isometries. Sorry, in this result, plane wave is not conformal manifold, it is a Lorentzian manifold. And when I say that Lorentzian manifold is homogeneous, it means that it is homogeneous with respect to the isometric groups. Wait, I will speak about. We consider conformal groups of conformal metrics, but this result is about isometries, about concrete metrics. So on general plane wave may be written as like that, but if it is homogeneous manifold simply connected, then there exist global coordinates, and metrics are written like that. And isometric groups are transitive only in those two cases. And here is the main theorem. So suppose that we have a simply connected, non-conformally flat, conformal Lorentzian manifold, and suppose that this manifold admits an essential transitive group of conformal transformations. Then there exists a metric G in this conformal class such that mg is a complete homogeneous plane wave. So this assumption that manifold action is essential, it is important because otherwise we just have some isometric group of some Lorentzian space, but there are more Lorentzian homogeneous space. This is some rigidity result. And another result is that when we have a simply connected non-conformally flat homogeneous plane wave, then the group of all conformal transformations consists of homotheties. It is one-dimensional extension of the group of isometries. This is not just connected group, but the full conformal group of full conformal transformations. In fact, in this work, they proved that the Lie algebra of conformal Killing vector fields, so the Lie algebra of the Lie group of conformal transformations, it is one-dimensional extension of isometry algebra, of Killing algebra, and this is generalization, some extension of the result. Now I'm going to explain the proof of the main result. I will need some notation. In fact, there is a lot of linear algebra used in this proof. So we denote by V the Minkowski space, and we consider it as a tangent space to some Lorentzian manifold. No, we pick some metric from the conformal class. So Witt basis. What is a Witt basis? Such basis of the Minkowski space, P, E1, and so on, En, Q. So vectors E1 and so on, En, they are also normal. They are also orthogonal to vectors P and Q. And both vectors P and Q are isotropic. They are isotropic, and the scalar product of P and Q is 1. And vectors E1 and En, they span Euclidean space. Euclidean space. Now we will identify B vectors with the space of B vectors with the Lorentzian Lie algebra. So when we have bivector, then we consider its action of vector Z and obtain another vector. So this is the element of the Lorentzian algebra. We obtain this identification. And when we fix the Witt basis, then Lorentzian Lie algebra can be decomposed into 4 types. Those are vector subspaces. Here in the brackets are PHQ plus SOE. This is maximal reductive subalgebra. And those are, okay, those are commutative subalgebras, but this is direct sum of vector subspaces. And here, description of the isometry Lie algebra of a homogeneous plane wave, or in other words, Killing Lie algebra of Killing vector fields. But it has the following expression, again from the paper cited above. This is known. So we have Lie algebra of the isometry group. So this is a stability subalgebra, the Lie algebra of stability subgroup, and V some complement is chosen V. This is just complementary vector subspace. This decomposition is not reductive. Now the stability subalgebra, it has this form K plus P wedge E, where K subalgebra of SOE consisting of elements that commute with B and F. P wedge E is just from here, from this decomposition, because this is decomposition of the Lie algebra SOV, and this isotropy subalgebra, it is contained in the Lie algebra SOV. And K acts on V in natural way. Lie bracket of K and V is subset of V, and other Lie brackets are given here. What is here is some parameter lambda. It is 1 for spaces of type B, and it is 0 for spaces of type A. Next, proof of the main theorem, we need some three lemmas. So we first suppose that we have a connected homogeneous conformal manifold, and suppose that we have some Lie subgroup G tilde of the Lie group G, which has open orbit. It has open orbit, and if the stability and stability subgroup is contained in the orthogonal group, then of course when stability subgroup is contained in the orthogonal group of the tangent space, then we have invariant metric on the corresponding homogeneous space. But here it is important that this invariant metric is a restriction of some metric from the conformal class. So again, G tilde here, it has open orbit and it preserves some metric. So another lemma is the following. So suppose that we have, just very general, suppose that we have connected homogeneous manifold, and if we have a normal subgroup F, normal subgroup of G, and it has an open orbit, then in fact F acts transitively on M. So in fact this orbit U is the full manifold. This is another lemma we need. And finally the following lemma. So suppose that we have homogeneous conformal Lorentzian manifold, and suppose that we have normal Lie subgroup, which also acts transitively on M, but it acts by isometries of some metric G of C. Then group G acts by homothetic transformations of G, the whole group G. Here is important that F is normal subgroup and it consists of isometries of G. So those three lemmas will be important. Now, again, let me recall what is going on. We have manifold M, group G, we have conformal metric, conformal class of matrix C on it. So G acts transitively, essentially, and C is not conformally flat. So H, we have the isotropy representation of the group H, and it should be faithful, so it is injective. V is a tangent space to the manifold. So Lie algebra of H may be identified in this case because J is injective with subalgebra of COV. And this is conformal Lie algebra. It is direct sum of the one-dimensional commutative subalgebra spanned by the identity transformation and by the, this case, Minkowski Lorentzian Lie algebra. And where do we need, we use assumption that the action is essential. Since the action is essential, H is not contained in SOV. If there were in G invariant metric in the conformal class, then the stability subgroup would preserve this metric, and it would mean that H is contained in SO or in the OV, in the pseudo-orthogonal Lie group. So H is not contained here, but we may consider intersection with A of H with SOV and denoted by H tilde. And then, since projection to identity element is non-trivial, there exists some element D in the stability algebra H of the form identity V plus some C from SOV. And so we get decomposition H equals to RD plus H tilde. This is one-dimensional ideal. It may non-trivially act in H tilde. And so it's possible to choose some complement vector subspace V in Lie algebra G complement to H. So we have such decomposition. This is in fact direct sum of subalgebra H and some vector subspace V, or H consists of three forms. So our aim would be to find the form of D, what is D, and to describe H tilde. So in fact, find the Lie algebra G. So this decomposition is not reductive. Yes, no, but it is maybe assumed to be invariant with respect to the maximal reductive subalgebra. H tilde is contained in SOV. This is Lorentzian Lie algebra. So the subalgebra H tilde is not reductive. So now we prove we are going to find the form of D. First of all, we prove that it is not possible that identity belongs to H. So we prove that if this element belongs to H, then MC is just conformally flat. But we assume that it is not conformally flat. And just maybe, at least I will explain proof of this lemma. And there are many different lemmas that are proved in the same way. So we have, if H contains this element, H can be decomposed in this way. Now, if identity transformation commutes with H, so there is an invariant subspace of G B, which is complementary to H. And it is identified with H. So this element identity annihilates H and acts on V as identity transformation. But this is the element of the Lie algebra, so it is a derivation of the Lie algebra. And by this reason, we get the following conditions for the Lie brackets. Now, we consider subalgebra G tilde. It's not written here what is G tilde. G tilde is just H tilde plus V. We see that it is Lie subalgebra. Corresponding subgroup of G is normal. And since G tilde contains V, this G tilde has open orbit. It has an open orbit. And by the previous, yes, it is normal. It is normal subgroup, and it takes transitively on M. And so G tilde acts by isometries of some matrix from the conformal class. But for homogeneous space with such brackets, VV, it is reductive homogeneous space. It becomes Riemannian reductive homogeneous spaces. But when we have such brackets, it means that the homogeneous space is flat. So metric G is flat, space is conformally flat, and this is contradiction. So it's not possible that H contains this identity. So D element identity is not contained in H, but in H is contained some element D of the form identity plus C. C is some element of the Lorentzian Lie algebra. And the problem is to first task is to describe D. And it depends on the description of C. And C is element of the Lorentzian Lie algebra. There is a description of such elements. There are three possibilities: elliptic, hyperbolic, or parabolic. depending on how it looks like, this element C. So, for example, here again appears this with basis, and our aim is to prove, in fact, that the only case when the space is not conformally flat is this hyperbolic case, and when alpha is -1. Only in this case, space is not conformally flat. With all other assumptions, it becomes conformally flat. So aim proves that C is of this form. No, I have already explained. This is used that D belongs to H, and H is subalgebra of G. This is a Jacobi identity, and so very often we use eigenvalue analysis of this element D of its adjoint representation. I just will explain why in some cases we obtain conformally flat space. So suppose that C is hyperbolic, but it is defined by some number alpha. The C here it is alpha. Now this is maximal reductive subalgebra of H, and we may then change V in such a way that it is invariant with respect to this subalgebra, this action of this subalgebra. Now, if you consider such element D, where C is hyperbolic, so if alpha is different from ±1, then we obtain the following brackets. So this follows from the analysis of eigenvalues of D. So if alpha is different from those numbers, then simply Lie bracket of VV is 0, because how D acts on V. So V consists of P, Q, and E. This is a way, so eigenvalues of D on V are 1 minus alpha, 1 plus alpha, and some complex, yes, 1 plus some complex number. Now, and we can also eigenvalues of action of D on H also complex. And now eigenvalues of VV should be sum of two of those, and then never belong to, there are no elements with such eigenvalues. For example, P, Lie bracket of P and Q, it should have D eigenvalues 2. P has eigenvalue 1 minus alpha, Q has eigenvalue 1 plus alpha. Lie bracket of PQ should have eigenvalue 2, but there are no elements in the Lie algebra with such an eigenvalue of D. So this Lie bracket is 0, so we get again conformally flat space, except for those cases when alpha is different from this number. One example. So if alpha is -2, then again this analysis shows that Lie brackets should be like that. V is in V, VV is in H. So we get G equals H plus V. This is Z2 gradient of G. Lie bracket of H and V is in H, V, VH. So this is 0 part, 1 part. This is the gradient of G. It should, this is symmetric decomposition. This decomposition gives structure of symmetric space. And stability subalgebra H is contained in the conformal algebra. So this is symmetric space. This is structure group of conformal algebra. So it means that this symmetric connection is a well connection. It is torsion free, and it preserves conformal class of metrics. So we get such symmetric space, and thanks to very recent paper with Dikarev Schneider, there are no, if we have such symmetric well space, then in fact it is this well structure is closed. So it means that holonomy of this is contained in SOV. So again, it means that so Lie bracket of V of V should be contained in H tilde. In fact, we have just a Riemannian symmetric space, and again, in this case, it's possible to show that consequences that the space is conformally flat. So thus, what we have is that element D of this form, D identity V plus C, C is like Z minus P HQ plus C0. And what we know about H tilde 0, it is contained in SOV. SOV has such decomposition. This decomposition is D invariant, and D acting here has the following eigenvalue. So H must be just intersection, consists of direct sum of intersections, or H tilde consists of direct sum of intersections with those vector subspaces. And it's possible to prove that in fact H is like that. But still we don't know what are those intersections. We don't know much about this H tilde. Yes, what is important that conformal Lie algebra of homogeneous plane wave. Now again, homogeneous plane wave. It consists of RD plus isometries, and D is exactly of such form as we just obtained. Now, what we do? So again, we consider simply connected conformally homogeneous conformal Lorentzian manifold. We have proved that Lie algebra of this Lie group is of such form, G equals to this. V tangent space has such decomposition, element D. And now we know, yes, we have also this. So then we have that Lie bracket of V. V should be contained here. Okay, this follows from the eigenvalue analysis of the element D. Should be contained here. So if we denote this intersection by P which E1, we obtain this Lie algebra F hat subalgebra of G. It is this subalgebra, and so F hat is subalgebra. Again, it contains V. It contains tangent space in some sense. So by this reason, it has an open orbit. F has an open orbit. This Lie algebra F hat. And if we consider smaller subalgebra F of F hat, this is a normal subalgebra of F hat, and the difference is only element RD. It is contained in the stability subalgebra, so they have the same open orbit. But F then, by the above lemma, corresponding group to F, it consists of isometries of this open orbit U. F hat consists then of homothetic transformations, as we have proved. And okay, we have this Lie algebra corresponding to Lie group F, and we prove that this open orbit U is in fact the homogeneous Lorentzian manifold. Homogeneous. This is homogeneous Lorentzian manifold, and we prove that it is a homogeneous plane wave. How do we prove it? We just describe the structure of this Lie. We may describe the structure of this Lie algebra, and then using standard how this Nabinzu map compute show that there is a parallel isotropic vector field, and compute the curvature and prove that curvature tensor satisfies condition of the plane wave. But U is homogeneous, so we get homogeneous plane wave. But then, since we get homogeneous plane wave, this only open set of our manifold is this homogeneous plane wave. Now, then we obtain inclusion of our conformal Lie algebra. G is a conformal Lie algebra of the manifold that we consider. If we restrict, we may consider elements of G as vector fields. If we restrict that vector fields to open subset, then we get inclusion of this Lie algebra because restriction is injective. So, restriction of a conformal killing vector field to open subset is injective. So we get inclusion to this conformal algebra. But we know already the structure of this conformal Lie algebra. First of all, we know that it is just Lie algebra of homotheties. Because UGU this is already homogeneous plane wave, homogeneous with respect to isometric group. So we get such decomposition. So we get that H tilde is contained here in a K plus P, which is, this is very important because before we knew only that H tilde is contained here. We could not somehow prove that this intersection is trivial. Now we see that, and this is important, that this intersection is trivial. And now, before we consider what was in fact this F, what was this F? It was H tilde without this part, without this intersection. And now F hat was with, but now F hat before there was this part, we could not prove, we could not state that this part is ideal because of this. Lie bracket of this and this gives something here. We could not state it. But now when we know that this intersection is trivial, we know already here that or maybe here we know already that F hat is ideal in G, not just subalgebra but ideal, and F is also ideal. So now H is of this form, and F is ideal, and ideal, its stability subalgebra is contained is contained in the Lorentzian algebra. So corresponding Lie group is normal, and by lemma above, this normal group already acts transitively on M, and it acts transitively on M. In other words, this open set U that we just considered before, and that we proved that U is a homogeneous plane wave. Now M, U equals to M, so M is homogeneous plane wave. So this was our statement. Then there is a metric G in the conformal class such that manifold is homogeneous plane wave. The complete proof result. Of course, quite algebraic, but the main ideas were here. Here, first to prove that locally we have this homogeneous plane wave. Then using this, find some information about the stability subalgebra and get already final conclusion that open set that we consider in fact the whole manifold M, because we have action, we have normal subgroup which has open orbit. Above we prove that then such group acts transitively. So this is all. This is all. I stop here.
So that is a whole thing?
Yes.
Oh, I see.
I was trying to explain the proof of the main theorem. Maybe at least I open.
Yeah.
Show again the main theorem. This is the main theorem.
So the complete homogeneous. Of course, not of course. I think that's many people know Riemannian geometry more than Lorentzian geometry. So you also explain the example homogeneous plane wave. Why this theorem is such important for Lorentzian geometry? Why do you think that? Yeah, I'm just trying to understand that what is important Lorentzian manifold and why homogeneous plane wave is should be kind of the special topic.
Yes, well, of course, plane waves in particular is important. Just plane waves. For example, no, I don't know. There are many physical reasons why they're important, but at least because of the Penrose limit showing that along any geodesic of Lorentzian manifold, there are some limits which gives plane wave limits of Penrose. but no, I cannot say much
Yeah,
about.
I know that there is in audience many more expert on conformal Riemann geometry. So just so anybody has some common question?
Hi, Anton, can I ask a question? So you say that this class of spacetimes that you studied, it's exhausted by plane waves, but which plane waves actually appear in this classification?
Only
Because I think there are
homogeneous.
more.
Homogeneous with respect to the isometry algebra. I'm showing them here.
Okay, so that's the only condition.
Yes, because it must be homogeneous, and they classified, and so we were lucky because this result just was obtained last year that we used. Last November appeared this preprint in archive.
Yes,
We need this global result. This result, classical result by Blau-Olin, it was only a local result. They found those metrics. In fact, locally homogeneous. It means that we should consider Lie algebra of Killing vector fields, and local homogeneous means that if we restrict this algebra to a tangent space, at some point, then we get the whole tangent space. So they found those local metrics, and with co-authors, they prove that when we have simply connected homogeneous plane wave, then it is either space Rn plus 2 or just half of this place, and with one of those metrics. There are families of metrics because they depend on B and F, on some constant metrics. And we prove that whenever we have, again, our main result, whenever we have just any simply connected conformally, non-conformally flat, conformal manifold group, it is homogeneous with respect to transitive group of conformal transformations, then there is some metric G in the conformal class, such that MG, already know MG is some complete homogeneous plane wave. Complete, in fact, complete, it means that type A.
Yeah.
Right.
Those spaces.
So maybe I missed it in your presentation, but what role did the global simply connected condition play? Did it is
simply,
it? I was just wondering, like, if your result would be different if you were just considering local, like open neighborhoods, or it would be
local neighborhood. So if we should assume like it's written like here that our conformal killing Lie algebra. No, I think that we will get such local results, such local metrics, because almost all the time we are working with this Lie algebra of killing vector fields.
Okay.
So probably yes, probably already we could stop. We could stop then with this proof already with this lemma. You see, we get this for this open subset U, it is homogeneous variance and it is homogeneous plane wave. So here, instead of this lemma, we would have that U is a locally homogeneous. Space, and this is already all because locally homogeneous plane waves they were known already before.
Yes, so that's
we are working with this Lie algebra of killing conformal killing vector fields, so that would be an easier task.
So the lemma one is
thank you.
Lemma one, can you show me again? Lemma 0 exists a metric lemma one.
I don't know. So I think this lemma is this.
So because you didn't enumerate and then later. Okay, so that should be lemma 1.
This is.
Don't make it. So that you find some canonical form of the metric. Yeah.
Yes. So what is going on here? We we have this connected homogeneous conformal manifold. G acts by conformal transformations, it acts transitively. And it should not preserve the symmetric in the conformal class. It just preserves the conformal class. Now suppose that we have, generally when we have homogeneous space, then generally when we have invariant object, G invariant object on the homogeneous space, equivalent condition is that we have at the point some invariant object with respect to H. So H preserves the value of the conformal class at the point, so it is H is contained in CO in this conformal Lie algebra. Now suppose that we have small subgroup G tilde, which has just open orbit. It has open orbit, and it is its stability subgroup H tilde is its isotropy representation is contained in the orthogonal group. Yes. Then, of course, sorry, by this principle, as I told about invariant objects, on this U, there is G tilde invariant metric. But here it is more also important that this invariant metric, it is restriction of some metric, of some global metric from the conformal class. This we need, of course.
Yes. So
some relation of the metric which appears on U with the global metric. And then U would be the open set that we considered. In our group G, we have found some subgroup which has open orbit, and then we consider restriction of metric from the conformal class, and we prove that this metric, this restriction, is homogeneous plane wave metric on U. And this gives us a possibility to say something about G tilde, this subgroup which acts transitively, because we know what which group acts
transitively. So see that lemma 1, lemma 2 is a key technical lemma, and the complete
yes,
is
so
also
2 and 3. No, this is very general. We don't need any metric for this. So if normal subgroup of transitive group has open orbit, then this group subgroup.
Yes, so that's
but this is also interesting lemma. So we have manifold and conformal manifold. We have normal subgroup which acts transitively by isometries. Then group acts by homothety transformations, not just by conformal, but no, by special conformal. This is
now I understood.
Also very restrictive.
Yes, so that's a lemma. Last lemma 3 is the assumes the condition of lemma 1 here. And the transitively is 2, then it implies that the homogeneous.
Important is combination of this lemma 3 and lemma 1.
Yes.
And this lemma 1, because this U, if we know that G tilde is normal, then this U is just M. And then we have, and then we know that G consists of a homothety transformation.
Oh, thank you very much, Anton. Yeah, so let us take a speaker.
Thank you.